Hi, my name's Tim Larini, and this is my Capstone project. I made a website for the NTD Silicon program where I work at MIT, the Nuclear Reactor Laboratory. I'm the Silicon Program Manager there. It's one of the features of the research lab. We do transmutation doping of silicon. Along with other research at the nuclear reactor. So one of the this is the main website for the lab, and we only have a small little page in regards to the silicon program there. So I thought it'd be good to have a more comprehensive page to allow people to understand what that process is and potential customers to reach out. We do business with international customers in Denmark, Japan, China, who send us the silicon to irradiate. So I made this website here with a few pages giving information about the process. This is a picture of the core at the reactor. So this is the main page. Is a little description about the silicon transmutation doping. So it's used in the semiconductor industry. So they send us pure silicon ingots, which we then irradiate in our facility. We have a 4-inch and a 6-inch port, which we use to irradiate the ingots. And they go right by the reactor core and the neutron flux. Some basic parameters of our operation of the reactor. We operate at 5.7 megawatts. We're light water cooled, heavy water moderated. So we have thermal flux available for irradiation. We're certified ISO 9001. And then we have quarterly shutdowns for maintenance, which affects our ability to for production of the silicon. So it's always good for customers to know for scheduling purposes. If we come over here, this describes the actual process of doping of the silicon. So we'll receive an ingot up here in this blue graphic. They look similar to that. They're about 15 inches long and then 4 or 5 inch diameters. So basically we load those silicon ingots into cans and onto a conveyor system, which pushes the cans through a port, and they go right by the reactor and get into a neutron flux. So when the neutron radiates the silicon, creates basically your goal is to create a low resistivity. So the neutron's captured by a 30 silicon atom, which has 3% abundance in silicon. It releases a beta, and basically your silicon 31 transmutates to phosphorus 31. So essentially they'll send us silicon that has a natural resistivity that's higher than what their customer wants. So when they make the silicon, they can't make it exactly the resistivity it needs to be for conducting electricity. And it's used in stuff in like electric vehicles, solar panels, basically high current applications. So then transistors, diodes, stuff like that. So we receive this shows a little the process. We receive the ingots, and then we receive an order. Basically tells us what the requirements are for resistivity of the ingots. We'll receive, inspect them. We'll load them in a can. They'll be irradiated. then we unload them. One of the biggest issues with this type of work is we're dealing with contamination controls since it's a nuclear reactor. So we have to wear special protective clothing when we handle this stuff after it's been inside the reactor. We also have to wait at least 5 days for the radioactivity to decay before we can even unload the silicon, because those things are very radioactive after they've been irradiated. But after about 5 days, based on half-lives of the isotopes, that stuff decays away to safe handling levels, and we can basically ship it. So we unload it from the cans, and we package them up and ship them out wherever they need to go. And then there's other radiological guidelines we have to follow. And then people can come look here. This gives a visual of what the actual ports look like that the silicon goes through. So they're loaded into 400 millimeter cans and placed on a conveyor. So the conveyor is over inside this concrete shielding. So there's a load side and an unload side. So the cans are loaded onto a conveyor, and then they get loaded into an airlock, which is filled with helium to prevent production of radioactive gases. So once it gets loaded into the airlock, there's a pusher that pushes the cans along this port, and this port goes right through some of our shielding and right by the reactor. And this like pink region here that's a little over 2 meters long is the actual irradiation zone where the cans are getting irradiated. And then this tube is also rotated as the cans are being pushed through to help even out the neutron flux. So we have a very good flux, and also within 5% we can usually reach the target resistivity that these customers want, which is a lot better than other facilities. So once the cans, we also program a computer that maintains the speed that these cans are going through based on what the target resistivity is. So they'll push those along and they get unloaded on the unload side, and then they'll sit there for 5 days until we can actually unload these cans, and then we clean them, make sure there's no contamination left on them, and then we ship them out. There's a little table here that I made to show what kind of capabilities we have as far as irradiation. So we do 4, 5, and 6 inch, and then max diameter for those, length for the ingots themselves so they can fit inside our cans. And then this is approximately the quantities we can handle per year, and the flux profile of our 4 and 5 inch tubes. Then I put a little page here about the facility. It's also, I embedded a YouTube video that gives a tour of the reactor, so if anyone wants to watch that, they can get what the overall mission and goal of the reactor is and what the facility looks like. This facility has been around since 1958, so it's been around quite a while. And we obviously do a lot of research. The silicon's just one small aspect of it. I've been doing the silicon for about a year now. Put in a contact page, so if any potential customer wanted to reach out and get either more information or look at potentially working with us, and they could send this to us. That's about it. So want to try to get this up and running on our main page here, since there's not much here, just one little page about the neutron transmutation doping. Alright, thanks.